Good afternoon, everyone. Thank you for attending today our webinar titled How to Ensure Your Flex Circuit Quick Turns Will Not Get Delayed. My name is Ed McMahon, and I'm the CEO here at Epic. Before we get started, I just wanted to let you all know that you will be muted during the presentation. So if you have any questions as we move along, go ahead and enter them into the questions panel that's located in the webinar control panel. We will try to get to them at the end of the presentation. Now, if we don't have time to get to all your questions, we will be sure to reply back to you by email, and we'll make the answers to all the questions available. Also, we'll be recording this webinar and posting it, both the recording and the slides, on our website and YouTube channels for you to be able to share this with anybody else that you'd like. Our presenter today is Paul Tomei, and Paul is our Flex and Rigid Flex product manager, and he's got over 30 years of experience in this business. He's been involved in all aspects of the industry, including sales, engineering, and manufacturing. He's worked with many PCB and equipment manufacturing companies. He's also been the owner of his own engineering and test service bureau. So Paul comes to us with a whole lot of experience, and I'm sure he's going to share that with us today. Paul's main duty here at Epic is really overseeing our entire Flex and Rigid Flex product lines with a hands-on approach to customer technical support, as he's often directly involved in many of the more complex Flex or Rigid Flex projects from the beginning, conceptual stages, all the way through, in production, manufacturing, and delivery. Again, he works directly with customers on the design requirements and making sure that we troubleshoot any of the issues that happen prior to getting into manufacturing, so there's no delays. And that's a big part about what this webinar is about today, is we want to make sure that our customers have the opportunity to get their quick turns delivered on time. So without any further ado, I'll pass it over to Paul.
Thank you very much, Ed. Good afternoon, everybody, and thanks again for joining us. As Ed mentioned, the topic of today's webinar is how to ensure your flex circuit quick turn will not get delayed. So starting off, we see a wide variety of challenges in many of the designs that are submitted to us for manufacturing. We see those challenges arising from things such as the complexity of design, the fact that there's such a wide variety of available design options that can be applied, the mechanical bend requirements that our customers need can, in many cases, pose challenges. As we all know, the compressed engineering timelines in and of themselves create challenges. And we also see that with many of our customers, just the extent of the knowledge base that they have to work from can be a main source of these challenges. As such, the vast majority of designs that we see have technical issues. And I would arguably say we're in the 85 to 95% range. So once we've done our design review and we've identified these technical issues, that in turn then requires, in some cases, a very extensive Q&A session with our customer's engineering team to resolve these. As an end result of those conversations, data modifications may be required. In worst case scenarios, designs may have to be redesigned from virtually scratch. And all of this, in turn, generates additional design reviews, the end result being timeline delays in the project and releasing that quick turn to production. So in our agenda, we've defined 4 specific groups that we're going to cover today. The first being the manufacturability of the design, in many cases due to
Paul, I don't think your slide is moving forward. There you go.
My apologies. So moving forward in an agenda, we're going to cover 4 specific areas. Manufacturability, in many cases due to excessive complexity in the design, and can lend to potential yield issues in the manufacturing. We're going to talk about materials, specifically non-stock specific brands and thicknesses. We're also going to delve into functionality of the finished product, what the bend requirements are, what the electrical performance requirements are for the design, and the reliability of the finished products, both from a mechanical point of view and its bend capabilities and requirements, and in its electrical performance. So starting off with manufacturability, the first element, or I wanted to start off by touching upon the IPC 2223 design standard. This is a very inclusive design standard that covers a very wide range of design elements. And ultimately, it defines what the best design practices are, what the best Gerber layout practices are, and construction practices. The ultimate goal is to eliminate any short-term and long-term reliability issues. Now, because this is such an extensive document, we're not going to have the opportunity of delving into all of it. So we'd like to use a rigid flex as an example of what sort of elements IPC 2223 covers and addresses issues in manufacturability. So an example we have today, it's a 6-layer rigid flex with 6 layers in the rigid section and 4 layers in the flex. So some of the key elements. First of all, the flex layers are configured as 2 independent pairs of 2 with an air gap in between the 2. The second critical element of this configuration is the materials. Specifically, the flex cores are defined as being adhesiveless, and in the rigid sections, the lamination is accomplished by utilizing low-flow prepregs. The other key element in this construction is in the coverlays, where a selective coverlay construction is utilized. The coverlays are applied specifically and exclusively to the exposed flex sections. They do not extend into the rigid sections. And the last significant element of IPC 2223C as it applies to this example involves the Gerber layout element, specifically identifying that plated through holes or via holes have to have a minimum spacing to the transition from your rigid section to your flex section. All of these elements combined result in eliminate manufacturing issues and result in a completely reliable design. Next element of manufacturability that we encounter deals with the size of the part and the shape. Excessively large designs can create some significant challenges and in some cases may not even be manufacturable. Large designs will bring into play a significant amount of material and manufacturing tolerances, which may not allow for layer alignment, may cause assembly issues. There are definitely limitations in the size of parts that can be manufactured due to the tooling systems and the equipment limits. And ultimately, the raw materials are only available up to certain sizes, which may prevent excessively large parts from being manufactured. The second element of this is the shape. And we've seen some very, very complex flex and rigid flex configurations. And there are a large variety of reasons why, but to sum that up, not all configurations are manufacturable. Another element of manufacturing is the stiffener requirements, with stiffeners being a very, very common requirement in flex and rigid flex designs. Some of the items that we see are customers defining stiffeners that overlap with one another, which can create either challenges or manufacturing issues with trying to laminate those stiffeners onto the flex circuitry. We often see the stiffeners not matching the outline of the flex, which again, in turn, can create some significant challenges. And lastly, to a lesser extent, we do see some customers try to specify some very unique materials. Some of those materials we've seen glass, we've seen ceramics, difficult to manufacture, and from a flex manufacturing perspective, we just don't have the facilities to work with those materials. A couple of additional items when it comes to manufacturability is the minimum flex length that can be manufactured. This flex section requires coverlate to be laminated onto it. As such, in order to maintain the positional accuracy of the coverlay, there is a practical 3 millimeter length limitation. We've also seen that designs that do have flex lengths of less than 3 millimeters typically can't achieve the bend requirements that the customer requires. So it comes into play in two areas. The last element are pressure-sensitive adhesives, or in other words, known as PSAs. PSAs are very commonly used in flex applications to assemble the parts and hold them in place within enclosures. But it's important to note that there is such a wide variety of PSAs available out there, both with respect to their adhesive properties, to their thermal properties, some are even electrically conductive. Not all of these materials are stocked. In many cases, there are some very large minimum orders required for these adhesives. And another important consideration is that if the design has to go through an automated pick-and-place assembly process, very few of these pressure-sensitive adhesives are rated to withstand the temperatures of assembly reflow. So moving on to materials. The biggest challenge that we encounter is when a customer defines a specific brand and part number of material in their data set. It's important to note that not all suppliers stock all of the available materials. There are also geographical restrictions as to what materials are available. What you can purchase domestically may not be available offshore, and vice versa. The main difference between domestic materials and offshore materials is the format of the materials themselves. Domestic materials are typically available in panel form, while offshore materials are most commonly purchased and utilized in a roll form. This impacts the manufacturing methods that are used. So tooling systems, and manufacturing equipment that are configured to use panels don't work with rolls, and vice versa. Our recommendation to our customers is to define their material specifications by the IPC specification callouts, or if they're not sure, to state that they allow for equivalent IPC certified materials. Another element relating to materials that we encounter are designs that call out for excessively thick and or thin flex materials and copper thicknesses. Again, it's important to note that not all thicknesses, both thicker or thinner, are stocked or commonly utilized. In many cases, in the majority of cases, thicker materials can have a very negative impact on the mechanical capabilities, or the bend capabilities of a design, which in turn can negatively impact the reliability and ultimately have a significant cost adder to a design. Third section involves the functionality of the finished product, and this is an important element that we pay attention to during our design reviews. A very common scenario that we encounter is the customers the databases do not define what the bend requirements are in a design. They don't define whether it's a bend once to fit application or a dynamic flex. the minimum bend radius requirements are not called out, the bend locations are not specified. Without that information, we're not able to confirm that the customer's materials, construction, ultimately their design, is going to meet their requirements. So it's important information to have, but in many cases, as I said, not present in the data set, requires us to have communication with the customer in order to identify these requirements. The second element is controlled impedance. We find many designs where the customer has not defined impedance requirements. They don't give us the values or the tolerances that they require. They don't define the specific trace locations. This is something that we look for, but without it being clearly defined in the data set, it does create the opportunity that these requirements might be missed, and the finished parts end up not meeting their controlled impedance requirements, which obviously is a significant electrical performance issue. Last section we're going to touch upon today is the reliability of the finished part. Many designs that we see utilize ZIF, or in other words, zero insertion force contacts. This falls primarily under a Gerber layout issue. We don't very often see the connector make or part number being defined in the data set. The flex requirements are very specifically defined by the connector spec. The connector spec will define what the minimum cover lay opening is, what the minimum stiffener dimensions are, also identifies some very tight tolerances. The alignment of the contact fingers to the part outline is critical. The width of the part outline is critical, and the finger area thickness with the stiffener is critical. All of these elements are necessary to ensure that the flex circuit engages the ZIF connector properly and reliably, and is part of our design review to ensure that the Gerber layout was done correctly in order to meet these specifications. Another element, we touched upon this earlier on, is the material stack-up. We see many designs where the material stack-up and the configuration of the flex results in a thickness that may not meet the customer's bend requirements. And the end result or negative impact of that is the parts could actually start breaking when they're being bent to shape into the final assembly. Touching back on IPC 2223C, we mentioned the minimum space requirements for vias and plated through holes to the flex transition area. Critical to ensure the reliability, both short-term and long-term, of the finished part. This is not something that we will deviate from, because ultimately it's in the customer's best interest. Component area stiffeners. Again, we see this on a regular basis where stiffener requirements are either missing or incorrectly defined in the data set. Stiffeners are an important element in many designs because they help protect the solder joints of either the surface mount components or any PTH components or connectors. The stiffener is going to prevent the flex from being bent immediately adjacent to any solder joint, and will protect those solder joints from inadvertently being cracked open as a result of the flex being bent. Again, a very important element as to the reliability of the finished parts. Gerber layout can have an impact on the reliability. A few elements that we encounter on a regular basis. First being offsetting traces from layer to layer within a construction. A detail that typically pertains to designs that have extremely tight bend radiuses. But again, that is part of our review. Once we understand what the customer's bend radiuses are, we'll then take a look at the Gerber layout to see if the opportunity of offsetting the traces is present, and then recommend that it be applied. If a circuit has to change direction within a flexible area, then the best solution is to have the trace have a arced corner rather than a sharp 90-degree. Arcing the corner eliminates the creation of a mechanical stress concentrator, which could cause the circuitry to crack if it's bent to any significant degree in that area. And the last element is utilizing fillets at trace to pad intersects, again, from the perspective of eliminating mechanical stress concentrators and preventing any cracks from forming when the circuitry is bent. The last item here doesn't necessarily pertain to reliability, but is still an item that we encounter on a regular basis. Many of today's flex designs and flex designs utilize some very high density surface mount components. BGAs, O201s, even smaller passives, and so forth, which in turn exceeds the ability of coverlay to define the surface mount features. So a very common solution in the industry is to use a hybrid construction of coverlay and solder mask within a given design. You'll utilize the solder mask in the component areas to give us the definition for the surface mount components that we need for ease of assembly, and we'll utilize coverlay in the flexible sections. Very common requirement, but not typically defined in the supplied data set. It's a significant change to the design. We'll look at it, identify if it's required in our design review, then we'll go back to the customer and make the proposed changes, make the proposal as to what needs to be changed. So in summary, all of the items that we reviewed today are part of the design review process that we implement, and we do this both at the quoting stage and we verify all of it at the production engineering process. If we identify any of these items, it will most likely create a delay in the processing of an order. Any of these items have to be resolved to prevent negatively impacting the performance of the parts and the reliability of the finished parts. As such, one of the biggest recommendations we have to our customer base is that they work with their supplier during the design process to address all of these issues early on to eliminate them and prevent them from arising at the 11th hour of the order processing stage.
All right, well, thanks, Paul. Paul's going to review the questions that came in, and by looking at the list, he's not going to get to very many of them, but there's a lot, which is great. So we appreciate everybody participating, and what we'll do here is Paul will answer a couple of them, and then he'll go ahead and provide answers, and we'll post them online so everybody can see the questions and the answers. But I'll get to a couple of them here in just a minute. For everybody's knowledge, just want to briefly mention some of the other printed circuit board based products that we do. We've been around for 66 years now, and we do everything from just bare rigid printed circuit boards to our flex and rigid flex. And very similar to Paul, we have folks who are as technical as Paul is on all of these products. So a lot of what we do is working with our customers on the design, creating reliable designs, and then moving into production. And it's one of the things that's got us here for the last 66 years. So, any of these products here, we're happy to get involved with. We've got substantial experience, and then we have manufacturing both here in the U.S. And in lower cost areas as well. So with that, let's turn it over to Paul. What kind of questions you got?
Well, I picked up 3 questions. I looked at the questions more from what what are we most commonly asked? So one of them, and we talked about stiffeners and materials earlier on. So the question is, what are the most common stiffener materials and thickness used? For component connector areas, FR4 is by far the most commonly used and preferred material. Thicknesses are typically going to range from 0.5 millimeter to 1.5 millimeters. Polyimide, not so oftenly used, only used if there's really a significant restriction in the available space and is limited to thicknesses of, or if the thickness of the stiffener has to be 1/8 thou or less. The general rule of thumb from a design perspective is that a stiffener is better than having no stiffener. For zip connectors, the material is always polyimide. The thickness is going to vary depending on what's needed to meet the zip connector specification. Typically, it's going to range from 2 thou to 8 thou in thickness. Polyimide is also the preferred and only used material for this application. The reason being is it allows the stiffener is actually applied larger than the shape of the part, and when we profile or create the shape of the zip connector area, we actually cut the flex circuit and the stiffener simultaneously. This in turn allows the really tight tolerances required by the zip connector specifications to be achieved. A couple of the other materials that we encounter: aluminum for applications requiring heat dissipation, and on occasion stainless steel for component areas that require a high degree of support but have a very limited space for the components, or for the stiffener, I should say. Both aluminum and stainless steel can add a significant amount of cost to a design, however. Second question revolves around material thicknesses and what are the standard flex materials used in the industry. For the majority of the designs that we see, the flex cores themselves range from 1 thou to 3 thou. There are some suppliers that list 4 thou and thicker material, but they're very seldomly used because they're going to reduce the flexibility and the bend capability significantly. The thicker materials are also considerably more expensive, and while they may be listed on a supplier's website, in many cases they're special order materials, which can add a significant delay. Half mil cores are available, seldomly used, very specific applications. Again, they come at a cost premium. Beyond that, they can be a very significant challenge to handle through production. In many cases, you need to have your equipment and your procedures specialized to handle material that thin. 2 to 3 mil thick materials meet the requirements for the vast majority of impedance control designs. For coverlays, the typical range is 0.5 mil to 1 mil, with 1 mil being the most common. Minimizing the thickness of the coverlay is always a positive, as it allows for a higher degree of flexibility and capability. And lastly, for the copper, the two most common thicknesses that we see are 1/2 ounce and 1 ounce, with 1/2 ounce actually being the preferred, providing that there's no significant current carrying requirement that either 1/2 ounce or 1 ounce can't accommodate. We do see some 2 ounce. It is available. We do manufacture with it, but it does have a negative impact on the flexibility of the part. Greater than 2 ounce require specialized manufacturing processes, which are not generally available. On the other end of the spectrum, less than 1/2 ounce copper, for example, 1/3 ounce, 1/4 ounce, 1/8 ounce, are available, but are only used for extremely high density designs that have less than, in some cases, far less than 3 mil line in space. And again, they typically require a specialized manufacturing process, especially in the imaging and etching processes. Last question I have is, what impacts the minimum bend capabilities in the design? Simply, it's a function of the materials and the construction used in the design. There's nothing from a manufacturing perspective that we can do to alter that. IPC has specific rules. The general rule of thumb when utilizing 1/2 ounce or 1 ounce copper are for a bend once to fit application, the minimum bend capability or radius is 10 times the thickness of the flex, and that works for up to 3-layer flex designs. For dynamic bend applications, the minimum bend radius is actually 100 times the flex thickness, and this applies to 1- and 2-layer flex designs only. Thicker constructions, higher layer counts, thicker copper weights will all significantly reduce the minimum bend capabilities of a design. So again, we'd like to thank you for attending our webinar today. Any questions that you've submitted, we will review and respond back via email. We appreciate your time, and thank you very much.